Hi all, I am K. Surya working as Assistant Professor in the Department of ECE at SNS College of Technology. In this video, let us see about Parity Checker. So a Parity Checker is a combinational circuit that checks and verifies the correctness of the transmitted data by analyzing the parity bit, which is called as a parity checker. The main function of a parity checker is to detect errors that can occur during data transmission. Parity checkers are used at the receiver end of the communication channel. It receives the transmitted data from the communication channel, and that data includes the original message code and the parity bit. After that, the parity checker counts the number of ones in the data code and compares this number with the expected code to determine whether there is any error or not. If there is any error in the received data, the parity checker takes an appropriate action like request to retransmit the data. The parity checker is an essential component in the digital communication systems to ensure the correctness and integrity of the data. It also provides a simple and effective method for error detection. So there are two types of parity checker, even parity checker and odd parity checker. So the type of parity checker that verifies whether the received data is correct as per the even parity system is called as even parity checker. An odd parity checker is a combinational logic circuit that checks and verifies whether the received data is correct as per the odd parity system. So now first we'll see about even parity checker. So the even parity checker counts and verifies that the received data contains an even number of ones including the parity bit. In case of an even parity checker, if the number of ones is in the received data is even, then it is considered that the data is error free. If the number of ones in the received data is odd, then the parity checker shows that the data contains some error. So let us see how the even parity checker works. Uh, Consider a 4-bit digital code. So here the 0011, and we'll be having a parity bit, say 0. Having 0 as the parity bit at the LSB position, this code is received by the even parity checker. So 00110 is received by the even parity checker. The parity checker will count the number of ones in the code which is even. So in 00110 we have only 2 ones. So thus the parity checker shows that it is an error free code, and so the bit is 0. Similarly, consider 01011. So in that you have the number of ones as 3. So there is an error, and so the bit will be 1. So this is a truth table for parity, even parity checker. So it will be counting the number of ones along with the parity bit. So totally we'll be having 4 inputs and 1 parity bit. So we'll be having 5 bits. So in each and every code, it will be checking for the number of ones. If the number of ones is even, then there is no error, and so the output will be 0. And if there is an odd number of ones, there is an error, and so the output will be 1. So here A, B, C, D represents the original digital code, and P is the parity bit. And in the truth table, CP, if CP is equal to 1, there will be an error in the received code. If CP is equal to 0, then there is no error in the received code. So when we draw the Karnaugh map and simplify this, we'll be getting the expression as A XOR with B XOR with C XOR with D XOR with the parity bit P. So for that, you have drawn the diagram. So A XOR with B, the output is connected to again an XOR gate with C as another input, and A XOR with the output of the XOR second gate is A XOR with B XOR with C. Then the third XOR gate is A XOR with B XOR with C XOR with D, and the final XOR gate is CP, which is A XOR with B XOR with C XOR with D XOR with P, as shown here. So next we'll see about odd parity checker. So as you know, an odd parity checker is a combinational logic circuit that checks and verifies whether the received data is correct as per the odd parity system. Our parity checker here counts and confirms that the received data contains odd number of ones, including the parity bit. So in case of odd parity checker, if the number of ones received is odd, then there is no error in the code. And if the number of ones received is even, then it represents an error in the code that might be occurred during the transmission. So for example, you consider a code 01101. So here the number of ones is 3, so there is no error. Another code 01100. So here also the number of ones is even. So there is an error and your output will be 1. So here in the truth table, the ABCD represents the original binary code and P is the parity bit. So from this we can observe that CP is equal to 1 if the code contains an even number of ones, and hence there is an error occurred in the coding during transmission. If CP is equal to 0, the code contains odd number of ones, which represents that the code is error free. And when we draw the Karnaugh map and write the expression, we'll be getting A XOR with B XOR with C XOR with D XOR with P, the whole bar. So like the previous even parity checker, we'll be getting using XOR gates, and finally a NOT gate will be used here in order to provide the bar function. Hope you understood how the parity checker, even an odd parity checker works. Let us take up some assessment questions. Which error detection method consists of just one redundant bit per data unit? The options are simple parity check, two-dimensional parity check, CRC, checksum. Yes, the answer is simple parity check. Next one is, which gates are ideal for checking the parity bits? The options are AND, NAND, XOR, XNOR. Yes, in the circuit we are using XOR gate. So here the answer is XOR. Thank you for watching this video.